Tuulos, and I lead the machine learning infrastructure team at Netflix. And of course, like, I do assume that you know much about Netflix, and maybe you know that for the longest time we have been doing personalized movie recommendations, which is like everything you see when you log into Netflix.com, you see the TV shows and movies recommended to you. But that's only the tip of the iceberg. So these days we do hundreds of other different machine learning use cases that you never see on the service directly. Kind of the same situation at Verizon and many other companies. And in my presentation, I really wanted to highlight the question that, like, what does it mean to be a data scientist doing this work today in a modern company like Netflix, or it could be like probably like a similar situation at Verizon. And like, I know that it's a very similar situation at many companies where you are like working at. And like, we have been working on a solution that would like really like make life as easy as possible for data scientists. The solution is called Metaflow, and I'll be talking about that today. So, I mean, just to give you context, again, like from the eyes of a data scientist, I don't want to start like with the tech stack of all the different elements that like we have in our machine learning stack, but I mean, really like highlighting the types of questions that data scientists are facing today. And these are just like actual quotes from our machine learning infrastructure support channel, just to give you an idea, like what it takes to solve these questions in practice. So here, for instance, like we had one data scientist one day come into the channel asking the question that, well, I have this project like where my model is kind of a time dependent, in a sense that my today's model always depends on the previous day's model. So I need to like process it for consecutive days sequentially to kind of produce the right results. And like, how should I architect my machine learning project so that I can always do this and I can do backfills and so forth? And now, of course, like for many of you who have been maybe hand building these machine learning pipelines for a long time, I mean, this definitely sounds like a solvable problem. And like, there isn't kind of any rocket science about this. But one thing that's good to keep in mind is that at least data scientists at Netflix are highly experienced in doing data science. They typically have a PhDs in statistics, so they have a PhDs in machine learning, but they are not always highly experienced software engineers. So having questions like this about the basic software architecture and like, how should I be architecting my machine learning workflow so that I can accomplish things like this, is actually a very relevant question. And here, the important thing is that this has nothing to do with the model. I mean, the data scientist is fully capable of producing the model by itself, but the question is that, like, how do you architect the whole pipeline in such a way that you can produce like these sequential results or have these like time-dependent models? That's just one example. Another, like a very practical, like a mundane example that many of you may have experienced is that, like, today we have these amazing off-the-shelf libraries available. We can use TensorFlow, PyTorch, scikit-learn, XGBoost, and of course, like thousands of other smaller libraries in open source that are available in GitHub. And similar to what Taneli was saying, like, we don't want to restrict our users to use only a kind of a hand-created set of libraries, but we would like to enable them to use the latest and greatest what's available in open source. But of course, the downside of this is that many of these libraries are not production ready in a sense that, like, they would be like guaranteed to be stable. And like, for instance, in this one occasion, what happened is that we had a machine learning pipeline that was using this library called Fancy Impute. It's an open source library that you can use for data imputation, which actually, like, behind the scenes uses a convex optimizer in Python called CVXPy. And I think it was about a year ago, CVXPy released a broken version by accident. And that then, like, in turn, like, broke Fancy Impute, which then in turn, like, broke one of our like machine learning pipelines. And like, things like this, of course, happen all the time. And sometimes things break just accidentally. Or sometimes it might happen that you just want to upgrade from TensorFlow 1.14 to TensorFlow 2.0. And like, as you may know, I mean, that the APIs have changed quite drastically between those two versions. So you really carefully have to manage the upgrade, especially, let's say, if you have some workflows that want to upgrade and some others that don't. So like, now we are kind of having this conundrum that on the one hand, like, we have all these amazing libraries available, but if we employ all these amazing libraries, things can become quite fragile easily. So we kind of have to really think carefully about dependencies, which is, again, something that, like, people in software engineering world have been thinking about for a long time. But I mean, this is really, like, not something that they teach you at school, like when you're doing a data science degree. like now, all machine learning pipelines access data. So the data is really the lifeblood of all these pipelines. And one thing worth noting is Netflix is fully on AWS, and we store our data in Amazon S3. We have large amounts of data, like maybe not as much as Verizon, but I mean still like hundreds of petabytes of data in S3. And then we have various query engines like Presto and Spark that users can use to query the data. But occasionally it happens that, especially in machine learning workflows where you just want to ingest massive amounts of data, things can get somewhat slow. And like people have these questions that, okay, how do I make my Spark SQL query faster? Or how do I make my Presto query faster, and so forth? So that's a very valid question. And obviously, given how important data is to all these pipelines, I mean, like finding fast ways to provide data would be really useful. Now, when talking about hundreds of petabytes of data, of course, there comes the question of scalability. How do we actually scale these pipelines? And we are not talking about only building massive scale models, like individual models that might require parameter servers, that what Anneli was talking about, but also the situation that you have a set of models that you want to be building. Let's say you have a project where you want to build a separate model for every country, and like maybe for every country you want to do hyperparameter search. So maybe you have a 200 times 1,000, maybe you have a 200,000 models that you want to be building. So obviously you are not going to do this on your laptop. So how are you going to do it? It's a very good question. And now finally, imagine that like you get to the point as a data scientist that you have figured out the architecture, you have figured out the data access, you have figured out scalability, you have figured out dependencies. And like this used to be a situation that it took a quarter of like maybe 3 months, 4 months of time to get to this point that you have the first version that like you are ready to deploy to production. And now let's say that like happily you have been running this thing in production for like some time, and then suddenly something breaks. And of course, I'm sure that like many of you have been in this situation that you have had a machine learning pipeline that has been running fine for some time, and then suddenly it breaks. And why it breaks, of course, like typically might be related to data, maybe something changed in the data, or like maybe it is just so that like something changed in the platform, or some interaction of the tool. Like in this case, the data scientist had an intuition that it might be that the data size has just increased and maybe the containers are now running out of memory. And how do you debug issues like this? Good questions. And then at some point, I just like did an overview of the type of questions we received on our machine learning infrastructure support channel. And I think that this is a really enlightening view on like what does it mean to do real life data science in a business environment these days. And like the interesting thing here is that, well, of course, there's a huge bias here. We are a machine learning infrastructure team, so we don't get many modeling questions, but also our experience is that the modeling questions are the ones that data scientists are quite capable of answering by themselves. And the questions that they ask, and actually the most time-consuming part of like building these projects is oftentimes just like related to this kind of a mundane software engineering questions. How do I architect my code? How do I operate? How do I do dependencies, so forth? Now in this chart, the data questions are really underrepresented. I mean, data questions are probably the biggest category in practice. We just have like many different places where we answer these questions as well. So there's a bit of a bias in this data set. So now, about 3 years ago, we started asking ourselves the question that, okay, given that this is the state of the world, and like data scientists at Netflix are spending a lot of time navigating these questions and asking these questions, and it used to be so that they had to kind of like take these like different infrastructure pieces and like stitch them together by themselves and answer these questions by themselves. And we saw that they were spending too much time doing this, and we started thinking that like what would be the type of infrastructure that would help you. And now, the kind of a principled way of answering the question is first to realize that, well, there are multiple layers in this stack, and there are multiple interrelated problems. And if you look at like from the most foundational questions upwards, like all these machine learning pipelines access data. So there's the question of data warehousing. There are questions of how do you, once you have the data, how do you actually perform the computation? All machine learning models require some computation. All these pipelines require computation. Not only like we are running computation in sense of like just containers here and there, somehow we have to orchestrate these sequences of containers, like in the case of like having these daily models. So we need some kind of an orchestration system or a job scheduler. And well, now, I mean, like after we have all those pieces, somehow someone needs to define like what gets computed, which is the question of architecture. How do I architect my code? And again, I mean, it's not sufficient for us as a machine learning infrastructure team only to say that, okay, here's infrastructure, you go and figure it out. But given that data scientists are not engineers, and they shouldn't be, we don't want them to spend too much time on software engineering. We have to help them in architect these pipelines. Then now when we talk about software architecture, there's the question that like, how do I version everything? Like as software engineers, we know that we are supposed to be using things like Git for source control management. But I mean, when it comes to machine learning, it's not only about the source code that you want to version control. It's also about the models. It's also about maybe data. So how do you version like your code? How do you version your data? How do you version your model? I mean, like all good questions that we should be helping to answer. And then finally, when you move upwards in the stack, you start getting closer to the actual data science. How do I operate my modeling pipeline? And finally, how do I do feature engineering? You just like write one big function that does all the data processing you need. But I mean, there maybe isn't much structure like in the code per se. So some data goes in, you perform some compute, and data comes out. And that's kind of really the baseline. Now, we actually had people who had been doing this for a long time, and they came asking that, okay, should I structure my code? How should I architect my code? And like what Metaflow provides is that, like, well, I mean, we ask you as a data scientist to structure your code as a directed acyclic graph. And this is a very familiar idea. Many other systems do this, and this comes very naturally for data scientists. So we say that you can take the function, or maybe you can even take the code that you have written in your notebook, and you can just structure it as this DAG. So you don't have to change the code. There's no new paradigm, nothing like that. I mean, all we ask you to do is that you follow the syntax that you see on the right-hand side. So you can see that there's a one-to-one correspondence between the DAG on the left-hand side and the kind of the code on the right-hand side. So the nodes in the graph are just the methods of the class, and then we have the edges, the transitions between nodes, defined with the self.next function call. So you can define a DAG. So nothing too special about that. And there are many systems that allow you to do this. But as I mentioned, it's really about the stack. Like just doing this is not enough. Just like defining a workflow is enough. And one of the key things you have to consider is that, let's say, the question of scalability. How do you scale this up? And now let's say that you started like creating your project in a notebook, and like maybe you loaded data in a pandas data frame. And like you can handle, let's say, a 16 gigabyte data frame on your laptop. Maybe you have a 32 gigs on your laptop or something like that. And maybe that's 60 million rows, 1 kilobyte per row. And let's say that like you want to handle all members of Netflix. So today Netflix has something like, 150 million accounts. So maybe you want to load all of them in memory at once. So wouldn't it be nice if you get this like really big laptop, so you can have a 200 gigabytes of RAM to do this job? And now, well, magically we can't like ship you a bigger laptop with 200 gigs of RAM. But I mean, thanks to this, thanks to the container management systems and the clouds, like we can just ask that, okay, here's a function, let's say my function B, that just happens to require this much memory. And like now we can go to the cloud and say that give me an instance on the fly, just for this one function, give me an instance with 200 gigs of RAM. And we can do the same for CPUs, we can do the same for GPUs. And now the interesting thing, and especially given the fact that like we operate everything in AWS, you could be operating the same thing in GCP or any other cloud, is that now you pay only for the duration of that one function. So if you wonder that, okay, is this cost effective to use these big boxes? Remember that now, in contrast to the old clusters that were running 24/7, you are only like paying for the duration of that one function, which is quite remarkable. Now, this is vertical scalability. I mean, just give me bigger boxes. Another way of doing things is horizontal scalability. So I want to build more models. I had that one example where the data scientists wanted to build country-specific models. And like, here's that case that, like, let's say that we want to do some kind of a fan out. So here we are doing a fan out over, let's say, different parameterizations. We define a grid, X, Y, and Z. It could be any Python list. And then we just say that, can you like run the step A in parallel, like for all these different parameters, and that happens quite easily. And then let's say like after the system has computed all the results, you can just, let's say, choose the best model in the join step. So this way you can have arbitrary amount of compute running, let's say, in the container management systems without data scientists having to basically like worry too much about anything. Now I mentioned about the data access and the fact that this is oftentimes the bottleneck in these machine learning workflows. And now the really beautiful thing about like doing things, let's say in AWS, is that the throughput between EC2 instances, the compute instances, and now the data warehouse is really high. So we can get one of those large instances that typically provides 10 gigabits per second throughput between the data warehouse and the EC2 instance. And now instead of even going through these query engines like Spark or Presto, we can just pull the data directly to your machine learning workflow. And if there's one feature that has made our data scientists extremely happy, it is exactly this. That they can, instead of having to wait for maybe 20 minutes, getting the data set so that they can start doing modeling, now they get the data set directly, like extremely fast. And now you can imagine that, of course, like you can do this in a sharded fashion, like you can have even like 1,000 containers, like pulling the data from the cloud in parallel. And thanks to the amazing work that AWS has done, it actually scales and it works. So we are also not doing a distributed denial of service attack against a database or like a data warehouse that definitely, in many cases, wouldn't be able to handle the load. In many of these workflow engines, and there are, of course, plenty of them, you may have used Airflow before, maybe Luigi, there are like many others. One challenge is that like the user has to take care of this state transfer by themselves. So like in this case, imagine that like in the start step, I define some variable, like in this case, X, and like I want to use X in the A step. And now remember, based on those previous examples about the resources and so forth, now all these things like run on different containers, physically on different machines. So we are not talking about a typical Python process where everything is in the single process. So somehow we have to load and store data between these steps. And in many other frameworks, the user has to take care about this by themselves, maybe storing the data in a database or S3 again manually. But that's kind of something that's a bit of a cognitive overhead. But actually, that's not even the biggest problem about like just loading and storing data. The biggest problem is that like our experience has been that like whenever we ask the user to be explicit about the data they want to store, people tend to be very conservative. And that's again like something that I do feel that has materially changed, like with the clouds that are available these days. That the kind of the space, is for all like practical purposes, it is infinite, and like you don't have to be so careful about what you are storing. Especially keeping in mind that it's really the human time, the kind of the productivity that is so much more important and so much more expensive than just like storing a few bytes in some persistent store. So now what Metaflow does by default is that when you do that self.txt, we actually persisted it automatically. We have a kind of a content address storage, so we don't store duplicates, but we store every single self.whatever, like including the models, everything in Amazon S3. And I will show you later like why this is super useful, but just to give you an idea, this is super useful when things fail and you need to understand what was the state of let's say your machine learning workflow before things failed. And to be able to recover the state is extremely valuable. And again, it's one of those moments when things fail at 4 a.m. that you really thank that this feature exists, because we used to have these situations that the data scientists built a workflow and then it failed, and of course the data science never expected that anything would ever fail. And then like when we are debugging, like there was no way to understand like what was really happening. So having this feature is really handy. And another interesting side effect of having these artifacts is that all those artifacts are basically immutable data blobs, like even all the models and so forth. They are immutable artifacts that we store in S3. We can give them an ID. We can give them a unique ID. And now like we can keep track of what workflow and who produced what. And this is our way of doing experiment management and managing lineage in these machine learning pipelines. We can keep track of exactly the models, the versions, who produced what, like all the way from the data sets to the deployed models. So like in this case, we can organize things in namespaces, and then like this is the Python API that we expose to the user. So you can ask any other persons that like give me the latest like a version of the model by my colleague, or like I want to look at the tags, like kind of what's the kind of the latest promoted version of my thing. And this way, like everybody at Netflix is a very transparent company, has access to everybody else's results in one unified manner, which is really powerful. Now, how we actually like allow people to kind of inspect these results is mainly through Jupyter Notebooks. So one interesting thing is that this far we haven't had any GUI per se. Like we realized that we support really hundreds of different use cases, from computer vision to natural language processing to classical statistics. So it's very hard to have a one-size-fits-all user interface, but like instead, I mean, all our data scientists are quite happy in using Jupyter Notebooks. So we just say that, okay, you can use Jupyter Notebook, you can visualize your models however you want. You can use all the tools that are available for plotting and so forth, and visualizations in notebooks. And I will actually, like, if I have time, I will show you a quick example how that works. But before showing that, I just wanted to highlight this thing, which is related to dependencies and this issue that I mentioned earlier with fancy impute and convex optimization, like in Python. And now the question is, okay, so since we allow the user to specify arbitrary Python code in these steps, how do you actually define the dependencies you need to use? Let's say one of the steps uses TensorFlow, maybe another step uses fancy impute, maybe another step uses XGBoost. So how do you do that? So we exposed this decorator called @Conda, which uses the open source Conda package manager. It's really pretty popular for data science in Python. And what we do is that we basically create a virtual environment, kind of a mini container, if you will, like for every step separately. And we instantiate the environment with the exact dependencies you have. So that if you say that you want TensorFlow 2.0, that's exactly what you will get. And you don't have to worry about anything else. And now I know that many of you, of course, like do similar things using Docker containers, which is quite fine, except that like, well, I mean, then you kind of have to write the Docker files by hand. And like, especially if you start having a different Docker container for every step in your workflow, I mean, you end up having many images, and now you kind of have two problems, since you have to have a system to manage these Docker containers as well. So this is a very handy way to manage dependencies. Also, it guarantees a very high degree of reproducibility, because we persist the data, as I mentioned about the artifacts, we persist the code of the exact workflow you are executing, and we persist the environment. And once you fix the code, you fix the data, you fix the environment, you have a pretty like good reproducibility. It's not perfect. You can still have random number generators and other sources of indeterminism in your code, but I mean, it gets pretty far. I know that like I'm like kind of already out of time, but let me just like show you this quick example. I think it's pretty fun. So when you pip install Metaflow on your laptop, well, I mean, it comes with a set of tutorials. And I just wanted to highlight this one tutorial. You can definitely do this at home just by pip installing Metaflow, but you don't have to pay too much attention in the code here. But like we do define different parameters in this workflow and so forth. But if we scroll down here a bit, there's this one step that produces an input dataset for our model. Let's say we are doing some movie recommendations here. And like we persist that like data frame or a list of movies in an artifact self.movies in that code. Now we can execute the code in Metaflow. It's as simple as run. You can do it locally. You can also like use different container management systems and whatnot. So you can find all that in the documentation. But now when we execute it locally, like we now have that metadata about that execution. We can see that, okay, we executed the playlist flow. And now what you can do is that you can open a Jupyter notebook. And in the notebook, you can use the same Python API that I was showing you before. You can just like import, like from Metaflow, import the Metaflow object, which gives you the full Metaflow universe, everything that everybody has been doing. And now you can look at the playlist flow, which was the flow that we were just executing. So let's take a look at that. And now within that flow, we can ask that, okay, what was the latest execution of that flow? And that's the timestamp that we just executed. So now we can take a deeper look at that run. And like every Metaflow run consists of multiple steps. Remember that DAG, so these are the steps, the nodes of the graph. And it was the genre movies that the step where we defined the movies list. So we can take a look at that. And that's a step. And like inside the step, we have a task. And like now we have all the data artifacts persisted, including that movies list. And now we can ask that, okay, so what's the list of movies that actually like was analyzed by this model? And like it gives us the list of movies. And now, of course, like although this doesn't seem like much, I mean, many of you have been practicing data scientists. You know that well, if you did all of this in a notebook, what you would be missing is that you don't get any of that experiment tracking. You wouldn't get persistent artifacts. You wouldn't get the scalability. And on the other hand, like if you did this only in Python, then like again, I mean, like you would have to build all these things by yourself. And especially again, I want to highlight that when things fail in production and when you are operating these pipelines in production, it's super important that like you are able to inspect the state of the workflow afterwards, and like you have this kind of the audit trail of everything that happened. So that's pretty much like what I wanted to highlight today. I just wanted to mention about like kind of give you a teaser of like some new features that will be coming out soon. So I don't know if any of you are users of R, but we actually do have like a somewhat like a thriving R community inside Netflix, and we have a layer of R that that's kind of a layer on top of Metaflow, and that we will be open sourcing like actually in just a few weeks. So if you want to do all the same things you saw here, like in R Studio using the amazing libraries that R has available, I mean that will be possible quite soon. Then another thing that like we will be releasing really soon is the question of how do you execute these things at large scale, like especially in an unattended manner, so that you don't click that run like by yourself, but let's say you have a model that you want to update every hour, every day, so forth. So we had worked together with AWS to provide integration with AWS step functions, which is basically a highly available, scalable scheduler or like kind of orchestrator by AWS. So now like how it works in Metaflow is that you write your code, you test your code locally exactly as I showed you before. But when you are ready to deploy something in production, like you can deploy it to step functions just with the single command sfn create. And like now it's the responsibility of AWS to make sure that your workflow always executes flawlessly. So that's pretty cool. Also, like we are working on a monitoring GUI. I mean, not to like provide universal visualizations. I mean, still notebooks are the best way to do that, but just to be able to eyeball all the executions. We have had some companies who are interested not only to run Metaflow in AWS, which is what we support today, but also on Google Compute Platform and using Kubernetes. So that's something coming up at some point. And one thing that I didn't touch in this presentation is the question of model hosting. How do you do real-time predictions? We have components for that like we will be talking more later. And then like something that I'm personally super excited about is the question of these fast data tools, and like how do we make it even easier for people to deal with this like kind of a medium-sized data sets, talking about terabytes of data in Python processes. And we are collaborating with the Apache Arrow project to kind of provide really efficient abstractions over in-memory data frames. So that's pretty much all I had today. So if you are interested in Metaflow, I mean, you can find us at chat.metaflow.org. Metaflow.org is the home page of the open source project, and you can definitely ping me. You can see my information there in the lower